Hello everyone and welcome back to Math Made Easy. So far in this numerical analysis course, we have completed the major methods for solving systems of linear equation. We started with Gauss elimination, Gauss-Jordan elimination, LU decomposition, and then move forward to iterative methods. Jacobi methods, Gauss-Seidel method, successive over-relaxation method, and finally the Thomas algorithm for tridiagonal systems. And with that, we have completed the solution of linear equations section of our roadmap. Today, we are beginning a new section of numerical analysis, the interpolation. Now, exactly do we mean by this interpolation? Suppose we know the value of a function at a very few particular points, but we don't know its value at a point lying between those known points. For example, suppose we know that this f1 value is 2, f2 as 5, and this f3 as 10. But we want to estimate this f of 1.5. How can we do that? If the function itself is not known, we can't simply substitute 1.5, no? Instead, we use the available data points to construct an approximate function that passes through these points. And this process is called interpolation. And today, we'll study our first interpolation technique, that is Lagrange Interpolation Method. We will understand the basic concepts of interpolation, derive its formula, and discuss its algorithm and solve a complete numerical example. So let's just begin with the definition. With this, interpolation is actually the process of estimating the values of an unknown function at a point lying within the range of the given data points. Suppose we know this x0, y0, this x1, y1, this x2, y2, and up to so on. And we want to estimate the value of a y at some point x lying within this given range. We construct an approximate function, usually a polynomial, that passes through the known data points, and then we use that polynomial to estimate the unknown value. Now, suppose we have this x and fx as this 1, 2, and 3. And the fx values 2, 5, and 10. And if we want to estimate this f of 2.5, then 2.5 lies between this 1 and 3. Therefore, this is an interpolation problem. Now, there is another term you must know, which is extrapolation. The difference is based on the location of the point where we want to estimate the value. If the required data lies inside the range of known data, we call it interpolation. And if the required point lies outside the range of the known data, we call it as extrapolation. For example, given data from x equals to 1 to x equals to 5 and estimating the value of f3 is interpolation. But if we are estimating this f of 7, which is known as extrapolation. So remember, the point is, if we want to estimate the value of the function inside the data range, it will be interpolation. If it is outside the data range, it will be extrapolation. Now you may wonder why interpolation is necessary if the function itself exists. In many practical situations, we don't have the complete mathematical function. Instead, we have only this discrete data. For example, like experimental measurements or temperature readings, population data, pressure measurements, or numerical simulations. Suppose experiment gives us values that is x equals to 0, 1, 2, or 3. But we need the value at x equals to 1.6. So interpolation allows us to estimate that missing value without knowing the complete underlying function. So suppose we have this n plus 1 data points now. That is x0, y0, x1, y1, and up to xn, yn. Now we want to construct a polynomial Pnx of degree at most n, such that this Pnxi becomes yi for every given data point. So this Pnx0 becomes y0, this Pnx1 becomes y1, and so on. Now the question is, how can we construct such a polynomial? And one powerful answer is the Lagrange interpolation formula. Now the central idea of this Lagrange interpolation is to construct these special polynomials called as Lagrange basis polynomials for the data points as x0, x1 and up to xn. And the ith Lagrange basis polynomial is Lix, to product of x minus xj whole divided by xi minus xj from j equals to 1 to n, where j is not equals to I. Now don't worry if this expression looks complicated at first. We'll understand exactly what it means. And the important property of the basis polynomial is this Lixj equals to either 1 or 0. 1 if I equals to j, and if 0 and if I is not equals to j. Now this is the key property that makes Lagrange interpolation work. Now understanding the basis polynomial. So suppose we have 3 points as x0, x1 and x2. Then this L0 x becomes x minus x1 into x minus x2 whole divided by x0 minus x1 into x0 minus x2. And similarly, we get this L1x equals to x minus x0 into x minus x2 divided by x1 minus x0 into x1 minus x2. And this L2x becomes x minus x0 into x minus x1 divided by x2 minus x0 into x2 minus x1. Now notice what happens at the data points. For example, this L0 x0 is 1, but this L0 x1 is 0 and this L0 x2 is 0. Similarly, this L1 x1 becomes 1 and it becomes 0 at the other 2 points as well. And this allows us to select exactly the required yi value at each data points. Therefore, this interpolation polynomial becomes this Pnx equals to summation of yi Lix starting from I equals to 0 up to n. Or explicitly you can say this Pnx equals to summation of yi product of x minus xj divided by xi minus xj starting from j equals to 0 to n, where j is not equals to y, and this I is starting from 0 to n, and this is the Lagrange interpolation formula. Now for the 3 data points, if we have this x0, y0, x1, y1 and this x2, y2, the formula becomes this p2x equals to y0 times x minus x1 into x minus x2 whole divided by x0 minus x1 into x0 minus x2 plus y1 times x minus x0 into x minus x2 divided by x1 minus x0 into x1 minus x2 plus y2 times x minus x0 into x minus x1 divided by x2 minus x0 into x2 minus x1. And this is a form you'll most commonly use in numerical problems involving the 3 points. Now there is one more advantage of this Lagrange method that you should remember. Unlike the Newton's forward and backward interpolation formulas, Lagrange formula doesn't require equally spaced values of x. The x values can be unevenly spaced. For example, we can take this x as 1, 1.5, 2.7 or 4.2 and can still be used directly in Lagrange interpolation. And this makes the Lagrange interpolation particularly useful when the data points are unequally spaced. Now let's just summarize the whole algorithm. Just need to write the given data points, this x0, y0 up to x and yn, and then identify the value of x at which interpolation is required. Now construct each Lagrange basis polynomial, that is Lix equals to product of this x minus xj divided by xi minus xj, where j is not equals to I, and then multiply each base polynomial by its corresponding yi. And finally, add all the terms and evaluate the resulting polynomial at the required value of x. So now that we understood the theory and the derivation of the Lagrange interpolation method, it's time to apply it on an actual numerical problem. We'll begin with a simple example so that you can clearly understand the mechanics of the formula. And then we move to a problem with unequally spaced data where Lagrange interpolation becomes particularly useful. So we have this Lagrange interpolation problem where we need to estimate this f1.5 from the following data where we have this x and fx values. X is 1, 2 and 3 and fx is 2, 5 and 10. Now we have this x naught value as 1, y naught as 2, x1 as 2 and y1 as 5. This x2 as 3 and y2 as 10. And we need this x equals to 1.5. And using the 3-point Lagrange formula, we got this p2 1.5 equals to twice of 1.5 minus 2 multiplied by 1.5 minus 3 divided by 1 minus 2 into 1 minus 3 plus 5 times 1.5 minus 1 into 1.5 minus 3 divided by 2 minus 1 into 2 minus 3 plus 10 times is 1.5 minus 1 into 1.5 minus 2 divided by 3 minus 1 into 3 minus 2. Now calculate each term separately. First term you have, second term you have, and third term you have. Therefore, it becomes this p2 1.5 as 0.75 plus 3.75 minus 1.25 and hence becomes 3.25. Hence, you get your f1.5 is approximately 3.25 now. So what have we actually done? We didn't know the exact function. We only knew three of the values as f1 as 2, f2 as 5 and f3 as 10. And using these 3 points, Lagrange interpolation constructed a polynomial passing exactly through the given data. We then use that polynomial to estimate the value at x equals to 1.5 and therefore this function value at 1.5 becomes approximately 3.25. And this is the fundamental idea behind this interpolation. So in this lecture, we introduced the concept of interpolation and studied our first interpolation technique as this Lagrange interpolation method. We learned the difference between the interpolation and extrapolation, understood why interpolation is useful when only discrete data are available, derived the Lagrange basis polynomials, and obtained the complete Lagrange interpolation formula. We also solved a basic numerical example stepwise, but there is much more to Lagrange interpolation. In the next part, we'll solve a more difficult problem, particularly one that involves there is much. So in the next lecture, we will move to the Newton forward interpolation method, where we will take advantages of equally spaced data and learn how the difference table makes the interpolation much more systematic. So thank you for watching and I'll see you in the next lecture.